application of BFRP bars for prestressing concrete members. The work I'll be presenting today has been done by some students in my research group. Prashant Motwani is actually one of my PhD students. And in addition to that, some parts of the work that I'll be presenting today have been done by my PhD student in collaboration with Queen's University Belfast. So the acknowledgements provided on this slide for Nichols Perogrambos and Professor Sue Taylor, who are actually members of the Queen's University at Belfast. So coming to the topic of my lecture. So first of all, we are all concerned about durability of civil engineering structures. So, and this slide actually gives you some numbers about the repair costs that are actually required both in US and in India to repair corrosion related damages in structures. And you can see that several casualties have also been reported in India due to the failure of structures caused by corrosion. So the solution for this is to basically reduce the corrosion, because it is not completely avoidable, so it cannot be eliminated, but it can be reduced by several techniques, and using pre-stressed concrete structures is one of those methods by which the corrosion that is prevalent in concrete structures can be reduced, because pre-stressing of concrete reduces the cracks in the concrete to a great extent, due to which the corrosion of concrete structures can be significantly reduced. However, we have noticed that even when we pre-stress concrete structures, the pre-stressing element is actually made of steel, which is prone to corrosion. And hence, the problem of corrosion still persists in pre-stressed concrete structures. So we can see that 20 to 25% of the total loss of corrosion can be avoided by using non-metallic pre-stressing elements like FRP. And actually, it is becoming more and more common every day, because even the ACI 440 code has given the guidelines for pre-stressing of concrete structures using FRP elements. And however, we have noticed that this BFRP, which is the basalt fiber reinforced polymers, are still not included in the ACI guidelines. And some of the reasons for that is because a lot of research has not been performed and it is not widely available. However, in countries like India, where basalt is readily available at several locations, this basalt fiber reinforced polymers can be a very good potential for replacement of steel strands in pre-stressed concrete structures. So let us first spend a couple of minutes on the fabrication of basalt fiber reinforced polymers bars. So basically, the starting material for these kind of bars is the molten igneous basalt rocks, which are actually which are actually passed through the CBF, that is the continuous basalt fiber technique, to produce the rovings of basalt fibers that you can see in this. Now, these basalt fiber rovings or threads are passed through the pultrusion line and combined with the polymer resins and under high temperature to eventually produce this BFRP bars. And you can see that the BFRP bars are having similar strength as compared to other type of FRP bars like the fiberglass, the carbon, and the aramid. And also we can see that the cost is quite low compared to the others. So it is similar to the cost of fiberglass reinforced polymer bars. So the various advantages of BFRP are: it is chemically resistant, and there are 50 to 30% higher tensile strength. The Young's modulus is almost similar to the glass fiber, and it is more resistant to ultraviolet reactions, higher fire resistance. It is non-carcinogenic and does not require any additives. And one of the disadvantages why it has not been very popular in the worldwide is because of the query for the source of the basalt rocks, which is not readily available in various countries. Now, coming to the research that has been done on the different types of FRP bars, where we can see that several researchers have and several guidelines have been provided for calculation of transfer length, which is an important parameter for pre-stressed concrete structures. So the transfer lengths for various types of FRP bars have already been researched, and recommended by several researchers. However, for BFRP, very limited research has been conducted, and one of these research has been conducted at the Queen's University, Belfast, by Philip Crossett, which is a PhD student of Professor Sue Taylor. So, in order to determine the transfer length, what Philip has done is there are no readily available mechanical wedge anchors for these type of bars, because these bars have very low transverse strength. So if you try to use the conventional mechanical wedge anchors that are normally used for the steel pre-stressing bars, they have a tendency to damage the bars at the anchor locations. So what Philip Crossett has done is he has combined the mechanical wedge anchors with an adhesive epoxy resin and used that to determine the transfer length of the pre-stressing bars. However, it has been noted that this high performance epoxy resin requires additional mixing and curing time and increases the overall production cost of the BFRP elements which are to be used in pre-stressing applications. So these are the basic motivations and objectives of my present work. So we know that PC members also, they degrade rapidly due to the corrosion of the steel strands. Hence, we wanted to investigate the behavior of concrete members which are pretensioned using BHRP bars. The second motivation is the commercially available anchor systems are not there for BFRP bars. So we wanted to investigate the performance of the readily available industrial anchors and propose modifications to improve the performance of these anchors and the efficiency of these anchors for BFRP bars. The third motivation for the present study is the recommendation of PC elements using FRP bars have not yet been included in guidelines such as the ACI 440. So we wanted to develop a test setup so that we can find out this design guidelines or develop these design guidelines such as the transfer length parameters or the transfer stage parameters associated with the BFRP bars. And of course, the last motivation is due to the low ductility of these BFRP bars or any other FRP bars. We all know that one of the major drawbacks of FRP bars is, compared to the steel bars, is the low ductility. And because of the low ductility, the high factor of safety needs to be incorporated in the design of structures which are used or which are constructed using these FRP bars. So the objective was to develop a smart FRP bar which is capable of sensing the stresses inside the bars and give early warnings, so that the factor of safety that is the large factor of safety that is required in the design can be reduced. So this is the basic outline of the presentation. It consists of an experimental part, some finite element investigation that we have done, and finally the development of the smart BFRP bars. The experimental part of the study has been divided into two parts. The first part is on the anchors that are used for pre-stressing BFRP bars. The second part is on that test setup that we have developed at IIT Bombay to pre-stress concrete members using BFRP bars and study the transfer stage parameters. The finite elements part also has been divided into two parts. The first part is on the mechanical wedge anchors that can be used for the pre-stressing of BFRP bars, and the second part is on the BFRP pretension concrete members in the test setup that has been fabricated at IIT Bombay. And finally, the last part of the presentation would be on the development of the smart BFRP bars, which has been done in collaboration with the Queen's University at Belfast. So coming to the first part of the experimental investigation on the wedge and the anchors for pre-stressing of BFRP bars. So as I said, the BFRP bars can be pre-stressed by two types of anchors. One is the mechanical wedge anchor and the other one is the bonded wedge anchor. So what we have done in this study, we have taken two types of BFRP bars which are provided by two suppliers, and both these BFRP bars have been manufactured using the open die pultrusion technique, and the claimed mechanical properties of the bars, two different diameters of them are provided by each of the suppliers. And the mechanical properties are shown in this slide. So it ranges between 920 MPa or to 1200 MPa for the tensile strength, and the Young's modulus for FRP is always lesser than the Young's modulus for steel. So it is somewhere between 40 to 50 MPa, and also the peak strain is somewhere between 2.5 to 2.8%. So as I said, the two types of anchor systems have been tested in the present study. One is the bonded anchor and the second one is the mechanical wedge anchors. So coming to the study on the bonded anchors. So the bonded anchors were fabricated as per the recommendations of ASTM D7205, which is for any standard FRP bars. And the material properties associated with the BFRP bars of 8 mm diameter supplied by the C2 supplier has been investigated. And so these pictures show you the fabrication of the bonded anchor using some glass sheets which have been wrapped around the bars, and then they have been heat treated, and eventually an aluminum tube has been inserted to develop these bonded anchors. And these are the specimens that have been tested using those FRP bars with the bonded anchors. So you can see the rupture of the fiber over the gauge length of the specimens. And so basically the fibers separate from the polymer resins and they rupture, causing the failure of the bar. So that is the desired failure. And these are the stress strain curves that have been obtained. So the average strength that we got from these bars was around 1100 MPa. And the modulus of elasticity that we obtained by interpolating the stresses and strains between 50% and at 50% and 25% of the ultimate strength was obtained as 44 GPa. And we can see that the fabricator claimed a tensile strength of 1200 MPa for these bars. So the anchor efficiency, which is basically the strength that we got by testing these bars using the bonded anchors, was around 94%. However, these bonded anchors are difficult for on-site installation because the fabrication procedure for these bonded anchors is quite complex and involved, and we do not have so much time and facilities at site to construct all these bonded anchors in large numbers. So hence the study has been further conducted on the commercially available mechanical wedge anchors for the rest of this project. So this is a test setup that has been developed at the Queen's University of Belfast by Prashant for testing the mechanical wedge anchors with two different types of the BFRP bars that have been supplied by the C1 and C2 suppliers. Here, in addition to the different types of bars, two different types of anchors, mechanical wedge anchors, have also been used in this test. So these pictures are showing the different types of anchors that have been used. So basically the category type 1 or the cat 1 anchor has of two different sizes for 8 mm and 12 mm diameter, which have been designated as type A and type B here. And the category 2 anchor, which has a longer holding zone, and it has a glass filled polymer wedge that has been used for also testing these 8 mm diameter BFRP bars. This second type of anchors is only provided for stressing of 8 mm diameter bars. So only the 8 mm BFRP bars provided by the C1 and C2 suppliers have been tested using this category 2 or cat 2 anchors. So 18 different specimens have been tested to estimate the anchor efficiency, and 3 specimens have been tested to study the relaxation loss or the long-term loading effect. And the anchor slips in these tests have been monitored using the digital image correlation technique as well as using linear potentiometers. The strains and loads have been monitored using strain gauges and load cells respectively. And a smaller loading rate than what is recommended by the standards of 0.008 strain per minute has been applied during the tests. So now let us look at the test results that we got. What we noticed is the BFRP bars are primarily failed in the anchor region for both the category 1 and category 2 anchors. And 2 types of failure was observed. One is the crushing failure, which is basically caused inside the anchor region due to the crushing of the BFRP bars by the serrated wedges of the anchors. And the other one is the frontal overload failure, which is due to the rupture failure near the, in the vicinity of the anchor outside the barrel. So this type of failure has also been observed primarily at the live end of the BFRP bars. And this table gives you the various strengths that have been obtained using the various combinations of the bars. So 2 types of bars, C1 and C2, And basically A and B are basically the two different diameters of C1 bars. And different diameters of the C1 bars, and C is basically the different type of anchor that has been used. So the A and B are category 1 anchors, and C is the category 2 anchor. A is for 12 millimeter diameter bar, and B and C are for 8 millimeter diameter bars. So the two different types of BFRP bars have been tested, and you can see that the rupture strength that has been obtained are actually range between 59 to 79% of the ultimate strength of the bar, whereas the anchor efficiency that was obtained with the bonded anchor was much higher. However, the ACI guidelines for using the FRP bars for prestressing application recommends that initial prestress of 50% of the ultimate strength has to be applied. So since these anchor efficiencies are above 50%, so hence these anchors can still be used. However, we are still conducting further research in our group to see if the efficiency of these industrial wedge anchors for prestressing BFRP bars can be further improved. Now we'll also take a look at the load-slip relationship as well as the stress and strain relationships of these mechanical wedge anchors that have been tested. So two different distinct regions have been obtained in the load-slip relationship, basically noted by the change in the slope of the curve. Now this initial slope is due to the seating process of the anchors inside the barrel, and thereafter the slope of this becomes steeper after the initial seating of the anchors inside the barrel. For the category 2 anchors, there was a third region which was obtained in the load versus slip relationship, and that was due to the plastic deformation of these anchors that was observed after the test. So basically these anchors are non-reusable. So once it is used for prestressing, they undergo plastic deformations and cannot be reused. And because of this, high fluctuations were observed in the load versus slip relationships. Now, as we predicted, the stress-strain relationship of these bars are observed to be elastic. So that means they don't have any ductility. So they keep on increasing and fail all of a sudden without giving any significant warning. We also performed the relaxation test on these BFRP bars, and we can see that at 1 hour, the relaxation loss obtained was 3%. At 24 hours, it was 8%, and it gradually reduced. The rate of relaxation reduced, and around 1,000 hours, it was around 12%. So, and based on this result, the 1 million hour relaxation loss has been extrapolated to be 18% without any slip of the anchor. So these are the variation of the strain with the bars, variation of the strain in the bars with the time. Now, as you observed that when we were testing these BFRP bars with the different anchors, it was observed that there was a slipping of these anchors during the test, and some of the specimen, because of which some of the linear potentiometers got damaged. Hence, second measurement technique, which is the digital image correlation technique, has also been used for some of the specimens where we have applied the digital image correlation technique at the live end anchor of 4 of the specimens, and we observed that the slips that were recorded by this digital image correlation technique were higher than the slips recorded by the LP. That is because the LP measures the slip primarily in one direction. However, the 3-dimensional effect is actually captured by the digital image correlation. And also we have noticed that if you look at these slip variations with time, for 2 of these specimens, we could observe the negative as well as positive slips. Now, this was because of the initial setting of the bars inside the anchors, because of which there was some reverse movement of the bars with respect to the anchors that was observed, which caused the negative as well as the positive slips to be recorded in these measurements. We also studied the microscopic image of the 2 types of FRP bars just to see the better fabrication procedure that has been applied to these bars. So we noticed that the bars provided by the C1 and C2 supplier had the diameter of fibers between of 15 micrometer and 10 micrometer respectively. The fiber to resin ratio for the two types of bars were 1.72 and 1.68, quite close. However, it has been noticed that the C1, the bar supplied by the C1 supplier has more uniform fiber distribution than the other bar. And also the sand that was that was coated on the surface were of size 30 micrometer to 60 micrometer on the bar supplied by the C1 supplier, and it was 150 micrometer to 250 micrometer on the bar supplied by the C2 suppliers. So with that, now we come to the second part of the experimental work, which is on the determination of the transfer stage parameters using the setup that has been developed at IIT Bombay. So this is the picture of the setup in which the BFRP bars are pre-stressed by applying some load on this beam. So it's a setup that is a self-balancing frame that has been fabricated, and it has two formworks in which the concrete beams can be cast, and this BFRP bars pass through this concrete beam formwork, and they are initially pre-stressed by applying some load on these beams to which these bars are anchored. So this is the loading rate that has been applied in the specimens. And after 2 hours of pretensioning, the concrete beams have been cast in the formwork which have been prepared along with the test frame. So these are the material properties of the concrete. So the material properties were tested at 3 days, 7 days, and 28 days. And the 28-day compressive strength, this is the cube strength, of course, and that is what we commonly use in India. It's around 45 MPa, between 40 to 45 MPa for the two specimens that we have cast. And after the concrete has developed sufficient strength, this formwork has been removed, and the BFRP bars, which were pre-tensioned, has been released, and once the bars are released, the prestressing force is transferred to these concrete beams. So now we'll talk about the various types of instrumentation that we have used in this test setup. So we have used linear potentiometers. We have also used the load cells for measuring the pre-tensioning load that we are applying on the BFRP bars. We have used linear potentiometers to measure the movement of the spandrel beam on which we apply the load to pre-stress the prestressing bars. And we also used linear potentiometers to record the end slips between the bar and the anchors, as well as the bar and the concrete. And also strain gauges have been used on the concrete beam and the BFRP bars to measure the strains after the release of the prestressing force. So two different types of strain gauge arrangement has been studied in this present project. So first one is an arrangement where most of the strain gauges are applied on the concrete beams, and only small single strain gauges were applied at the center of the BFRP bar inside the concrete, which is embedded inside the concrete. This was done to just check whether the prestressing force is effective inside the bar, and most of the strains were obtained from the strain gauges which were mounted on the concrete beams on both specimens of the concrete beam. A second arrangement of the strain gauges has been provided in the second batch of specimens that was cast. So this has additional strain gauges on the BFRP bars itself, because here we wanted to obtain the strain profile from the BFRP bars in addition to obtaining the strain profile from the concrete beam specimens. And however, please note that the concrete properties as well as the dimension of the specimens and the bar and the level of pre-stress that have been applied in these two batches are same. So this is the summary of the results that were obtained from these tests. So we could get relaxation of between 4 to 6% for the two batches. The Young's modulus was between 48 and 51. And however, for the first batch of specimen, the strain gauges were not used for measuring the transfer length. So we have only used the concrete strain gauges. So that gave a transfer length of 375 millimeters for a BFRP bar of 8 millimeter diameter. And for the second batch of specimens, the strain gauges that were mounted on the concrete unfortunately debonded, so we could not get the strain profile from the concrete surface. However, the strain gauges that were embedded or which were embedded on the which were mounted on the BFRP bars embedded inside the concrete, we got the strain profile, and the transfer length obtained from that batch of specimen was 325 millimeters. The end slips were also very nominal. It was between 1 to 2 millimeters. So this basically gives you an idea about the transfer length of BFRP bars is approximately of the order of 40 times the diameter of the bars, and the pre-stress losses here were between 12 and 14%. So basically, coming to the summary of the first part of the work, which is on the experimental investigation. So we conducted the anchor efficiency test of the mechanical wedge anchors and found it to be between 59 to 79%, which is still acceptable for pre-stressing applications because the ACI code recommends about 50% of the initial pre-stress of 50% of the ultimate strength, and the 1,000-hour relaxation loss and the 1 million hour predicted relaxation loss were between around 12% and 18% respectively. The transfer stage parameters, it was the transfer length for these 8 millimeter diameter BFRP bars were between 325 to 375. The end slips were nominal. The average bond stresses that were obtained was 1.8 to 2.6 MPa for concrete of having strength of 40 MPa. And the total strain loss was between 12% to 14%. Now coming to the next part, which is the finite element studies conducted as part of this research, first on the mechanical wedge anchor systems. So we have done some finite element modeling of this mechanical wedge anchors that we have tested at Queen's University, Belfast. And due to the symmetry of these anchors, only half model has been developed for these anchor systems. And we obtained a peak rupture load of 57 kilonewtons from the experimental results, and compared to that, the finite element result was quite close. So it gave a peak rupture load of 60 kilonewtons for these FRP bars. And the ultimate stress was also quite close to the stress that has been obtained from the experimental results. However, this ultimate strain was slightly higher. However, you can see from this load-slip relationship as well as the stress-strain relationship, they are quite close, and hence this model has been further used to conduct parametric studies for 12 other FE models that has been developed to study various parameters. So some of the first parameter that has been investigated is the length of the holding zone. So 3 different models with 3 different length of the holding zone of the anchor has been investigated, and the peak strains has been obtained as shown in this slide. And it has been obtained, it indicates that there is an approximate reduction of 50% of the peak strain when you change the anchor length from 45 millimeters to 95 millimeters. The second parameter that has been investigated is the initial position of the wedge. So 4 different initial position of the wedge as well as the setting load has been investigated, and it can be seen that the anchor efficiency is affected when the wedges are not properly installed. So basically this red line basically shows the properly installed wedge, and you can see that there are no initial slips that are observed in this anchor, and also the slightly higher strength has also been observed for this wedge. The third parameter is the clamping angle of the wedge. So 5 different clamping angles have been investigated, and we found that the compression force on these BFRP bars increases with the reduction of the clamping angle. So that is another observation that we made. So this is the black line is the one which is the least with the least clamping angle. So that has the highest compressive stress on, or the radial stress on these BFRP bars. So this is critical because as we mentioned, that the transverse strength of these BFRP bars is very low compared to the longitudinal strength. And finally, the fourth parameter that has been investigated is the barrel wedge configuration. So 3 different models or 4 different models have been investigated with different thickness of the barrels as well as the wedges. And these are the different plots for the von Mises stresses that have developed in the wedges with the distance from along the barrel length. And you can see that the standard category 1 anchor that has been used, it did not undergo any yielding phenomenon, and the stresses in the other configurations that were investigated were higher. So hence it was concluded that the configuration of the category 1 anchors are adequate for the pretensioning of the BFRP bars. Any change in the barrel and wedge thicknesses would result in higher stresses, which would cause the yielding of these anchors and the barrels. Now coming to the second part of the finite element studies. So this is on the test frame that we have developed at IIT Bombay. So the system has been designed as a self-restraining rig, and it has been fabricated with the readily available materials. A patent has already been filed for this system that has been developed, and it can be used multiple times, and it can be for repeated pre-stressing applications, and it can be transported from one place to another. It's a portable frame. And we have also performed, as I said, the finite element studies to improve or refine the design, and also to study the transfer stage parameters of this BFRP pre-stressed concrete beams. So this results that are shown here are basically for the design requirements. So the one of the back beams on which the pre-stressing bars or the BFRP bars are anchored showed yielding of the steel without any stiffeners. Hence, stiffeners have been added in this location, and the factor of safety has been of 1.25 has been achieved due to the addition of the stiffeners. So, and we can see the reduction in the stresses that generate after the addition of the stiffness or the strengthening. Also, the spandrel beam has been modeled, and additional stiffness have been provided based on the result to get a higher factor of safety, because this beam will be directly subjected to the load during the pre-stressing applications. Hence, a higher factor of safety has been achieved by providing additional stiffness, even though it was observed that these stresses in these beam did not reach yielding due to the application of the pre-stress. The BFRP strains and the end slips have also been studied from this, and it has been observed that the initial strain has been calibrated to match the experimental and the finite element results. However, the subsequent strains in the BFRP with time have not been calibrated. They have been obtained as the results have been shown from the experimental and the finite element analysis. And although the values did not match exactly, but we can see that the certain trains, which are basically due to the losses of what caused by the elastic shortening of the beam and the creep and shrinkage of the concrete, are all qualitatively predicted by both the finite element analysis and the experiments. And also, as I said, the FE model reported higher end slips. However, the pattern of the slip that has been obtained are similar and matches with the experimental results. Coming to the transfer length that has been obtained, the transfer length has been obtained using the strain gauges on the BFRP bar as well as the strain gauges on the concrete. So we can see here that the transfer length obtained from the strain profile matches well with the experimental results. And these are the strain profiles obtained from the concrete and the transfer length. So the transfer length obtained from the experimental analysis or the experimental study is 325. And this is from the strain gauges. So it is for 450 millimeter from the finite element investigation. However, as I said, there was debonding of the strain gauges on the concrete, so we could not get the experimental transfer length, but the finite element showed a transfer length of 460 millimeters, which matches quite well with the transfer length that has been obtained with the strain gauges on the steel on the BFRP bars. So the conclusions from this second part is that a robust nonlinear 3D nonlinear model for the mechanical wedge anchor has been developed, and parametric studies have been performed to study the effect of various parameters. And also for the BFRP pre-stressed concrete beams, a unique modeling technique has been developed to simulate the pre-stress transfer in the abacus, and a robust design of the test setup has been established using the finite element analysis. And the transfer stage parameters of BFRP bars have been evaluated using finite element analysis. Now coming to the last part of this study, which is on the development of smart BFRP bars. So as I mentioned, the FRP bars do not have sufficient ductility, and hence a large factor of safety has to be applied when they are used for construction purposes. And one of the solutions of avoiding this large factor of safety is the combination of FRP with the fiber-optic sensors, so that the stresses can be more accurately predicted in these FRP bars, and the factor of safety required can be less. So the working principle of the fiber Bragg gating, which is used in the fiber optic sensor, is the change of wavelength of light when it passes through some mechanical devices, and this change in wavelength due to the change of strain in the mechanical property or in the element is actually used to calibrate the strain that has occurred in the element. So that is the basic principle of fiber optic sensors which has been utilized in this study. So first we were using externally mounted sensors on these bars, and also we tried some surface integrated sensors which were installed by making a small V groove on the surface of these bars and installing these fiber optic sensors. However, we noticed that installation of these fiber optic sensors on the surface or inside that groove that has been created does not give high values of strain. It can measure the strains only up to 2000 microstrains because of the breakage of these fiber optic sensors, maybe at the anchor region. Hence, to avoid this, we have come up with a surface integration and we have come up with a technique to embed the sensors inside the FRP bars. So what has been done is the normal pultrusion line has been modified to install a BFRP creel, which basically combines with the BFRP fibers before it goes into the resin and the temperature chamber, and that is how the integration has been obtained. Now, once this BFRP bar is produced, then the fiber optic sensor needs to be connected to some adapters. So this is a small video that I have here to show you the integration of this fiber optic sensor with the adapters. To install a BFRP creel, which basically combines with the fiber. So this is a splicer that was used to obtain to connect the adapters with the fiber optic sensor which has been already embedded inside the BFRP bar. So once that adapter has been connected to this fiber optic sensor, then these adapters can be connected to the instrumentation systems, and any strains that are subjected on these BFRP bars can be recorded. So you can see it here, it is being recorded here. So that is how the integration of these fiber optic sensors with the adapters or the splicing of this fiber optic sensor has been achieved. And this shows you the distribution of the fibers inside along with the sensors. So the quality evaluation of the embedment technique was carried out using optical microscopy, and you can see that it has been, this fiber optic sensor has been integrated effectively and with the fibers of the BFRP bars. And also we have done some other tests. So we have basically tested these bars with some strain that has been applied on and measured also using linear potentiometers, and you can see that the strains recorded by the two measuring devices are quite close, although the strains recorded by the LPs are quite higher because the strain gauge that was used or the fiber optic sensor did not have the capability of recording higher strains. If you use a different fiber optic sensor which can record higher strains, that can be used to record higher strains in these smart BFRP bars. And so basically the summary of this part is the surface integration technique for embedding sensors was tested by making a V groove, but it was found that it is not, there are chances of getting damaged at the anchors. And so there is an improved manufacturing technique for smart prestressing FRP bar has been developed, and the lab investigation revealed that these smart bars are equivalent to the normal FRP bars in terms of the fiber distribution and also in terms of the properties that have been tested. So this is the overall summary. So first is the experimental investigation that was conducted on the industrial anchors to pretension BFRP bars, as well as the pilot test that has been conducted to cast the prestressed concrete beams with BFRP bars. And then a finite element investigation has been conducted on both the mechanical anchors as well as the test setup to study the transfer length, transfer stage parameters, which are important for developing design guidelines for this BFRP prestressed concrete beams. And finally, a smart BFRP bar has been also developed and tested, which can be used for practical implementation. So now the ongoing work that is we are carrying out is improving the efficiency of the mechanical wedge anchors for BFRP prestressing in concrete beams, and also use of smart BFRP bars in structural members. I'm sorry to have exceeded the time by some amount. That is all I have to present. Thank you.